Hey everyone, today's going to be the last day of going over a lot of chemistry review to lead into advanced chemistry and our first chapter. So let's go ahead and get started. If you remember last time, we were learning about the difference between ionic and molecular compounds. Then we briefly went over how do we make their formulas and how do we name them. One thing that goes in molecular compounds, though, is learning how to draw Lewis structures. And Lewis structures became a big thing. In fact, if you remember, one of the handouts I gave you at the beginning of the year was the Vesper handout, which has examples of electron groups, our bonding groups, lone pairs, what type of geometry they have, and some examples of what they may look like. And this is what we're going to work with today. So first and foremost, we have to understand the rules for drawing Lewis structures. The first thing to do is count the number of valence electrons for each atom and then add them up to find the total number of available electrons. A good example of this is if we're working with something like HCN. We know hydrogen is in group 1, so it gives 1 valence electron. Carbon can give 4 because it's in group 4. And then nitrogen can give 5 because it's in group 5, giving me a total of 10. The next thing you need to do is draw a skeleton structure. And we do this by determining who is going to be our central or our middle atom. Typically, it's the first element listed, or if you've been given carbon, carbon is almost 100% in the middle. We try to say the least electronegative atom. So here, HCN, my carbon's going to be in the middle, flanked on each side by a nitrogen and then a hydrogen. Remember, hydrogens and halogens are typically not the central atom, but there are instances where you will see halogens in the middle because they are less electronegative than the other atoms that are there. Step 3, place a line or a bonding pair between each of the atoms, and that's what I did here. I drew a line here and here to connect the hydrogen and nitrogen to my carbon. And remember, the line counts as 2 electrons. So I started out with 10, and right now I've used 2, 4. So I've used 4 electrons, and I've got 6 so far. Again, we're going to subtract that from the total number like I just did. Step 4 says place the remaining electrons around the outside atoms to satisfy the octet rule. And just to clarify the octet rule, this is where we want 8 electrons around all of our atoms. Hydrogen only requires 2 electrons, not 8. And the reason for that is because its closest noble gas is helium. Now, if there are any electrons that left over, we put them on the central atom. And the reason for that is because sometimes certain elements have expanded octets, and so it's okay to have more than 8 electrons around it. So what we're going to do up here is we put them on the outside first. So hydrogen's okay with just having 2. So we're going to put the remaining 6 on nitrogen. That leads us to step 5. Check to make sure everyone's satisfied by the octet rule. If the central atom does not meet the octet rule, we have to move a pair of electrons to make a double bond and even possibly a triple bond. One thing to note is hydrogen and halogens, and when I mean halogens is things like fluorine, chlorine, bromine, iodine, will not form double or triple bonds. So if we go back here, hydrogen is okay with the octet rule because it has 2. Nitrogen is satisfied by the octet rule because here it has 2, 4, 6, and then 8 from this line. But carbon's not happy here. It only has 2, 4, and it wants 8. So we have to take one of these pairs and make us a double bond. And when I make us a double bond, now I have such. Hydrogen's still happy, nitrogen's happy, but carbon's still not happy, even though it has a double bond here. So what we need to do is move another pair over and make a triple bond. And this leads us to the following structure. Hydrogen's happy, nitrogen's happy, and here you can see carbon is officially happy. 2, 4, 6, 8. So that's how we draw Lewis structures. So let's do a couple examples on our own. Here we have Lewis structures. Phosphorus is in group 5. Chlorine is in group 7, but there's 5 of them, so 7 times 5. And this gives me a total of 40. We don't have carbon here, so typically the first one listed is in the middle, which is going to be my phosphorus, followed by 5 chlorine. Right here I've made 2, 4, 6, 8, 10 bonds, and that's okay. This has an expanded octet. And then what we need to do is complete the outside first. So chlorine needs to have 8 total. It already has 2. So all the following can get 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So I've used all of them. I check, everybody's happy, we're great. Now if we go over here to Ni3, N can donate 5, iodine can donate 7, but there's 3 of them, so that's 21. That gives me 26 that I'm working with. Nitrogen will go in the middle since it is the first one listed and least electronegative. I've used 6 bonds, so that leaves me with 20. So I put them on the outside. When you make the outside happy, you're going to notice that you've only used 18 electrons. So I have 2 left over. Those 2 go on the middle. Now you check to make sure everybody's happy, and everybody is, so we're good. Down here, xenon is in group 8, so it can donate 8. Hydrogen, it has 7, and there's 2 of them, so that's 14. That gives me 22 that I'm working with. Here, we're going to see xenon in the middle, and while noble gases don't like to react, it will with fluorine because fluorine is so electronegative. So we're going to put fluorine on either side of it, and this brings us down to 18. Make the outside happy first, so 2, 4, 6, 8, 10, 12. Minus 12 will get me 6 left over. And all 6 of those, if my outside's happy, have to go on the middle. So that's going to give xenon more than 8, and that's okay because it has an expanded octet. And then our last one over here, carbon can donate 4, hydrogen donates 2 or 1, and there's 2 of them. And then oxygen can donate 6. So here we're working with 12 electrons. Note here I have carbon, so carbon goes in the middle, followed by hydrogen and oxygen. So that puts me down to 6 electrons because I've used 6 here. I'm going to put those all on oxygen. Hydrogen does not need them because they're happy with 2. Notice here I've got to check to make sure everybody's happy. Carbon is not happy. It only has 6 around it. So what we need to do is take one of these pairs and put them down on the carbon, and that will get us to the following structure. Note here that oxygen's happy with 8 and carbon's happy. Now, once we draw these Lewis structures, the easiest thing is to look on that VSEPR sheet that I showed you at the very beginning of this lesson. Here you can tell me what are the shapes of these different molecules. So for easiest thing to do is look at bonding versus lone pairs, and you're always going to be focused on this middle atom. So for example, here we have phosphorus. There are 5 bonding groups. There's no lone pairs, so 5 and 0 will tell me that this shape is going to be trigonal bipyramidal, bipyramidal for both my molecular and electron geometry. Over here, if I'm looking at it, I have 3 bonding groups and 1 lone pair. So 3 and 1 is tetrahedral for electron geometry, and molecular geometry is going to be trigonal pyramidal. Down here, I have 2 bonding groups, and 3 lone pairs. So if you see 2 and 3, that is trigonal bipyramidal. And in fact, my molecular geometry is linear. And last but not least, here I have 1, 2, 3 bonding groups because double and triple count as 1. So 3 bonding groups, no lone pairs. That means that this structure is trigonal planar for both my electron and molecular geometry. Then we go into hybridization. Hybridization has to do with the total number of electron groups. So what you're going to do is you're going to focus on the electron geometry. So we just classified that on the previous slide. So we can do that here as well. For example, we said that this geometry was a 5 and 0. So 5 and 0 will be a trigonal, so that's spelled wrong, trigonal bipyramidal. So that's an sp3d. So sp3d makes sense. 1s plus 3d plus 1d, that gives me 5 groups here. Here I have 1, 2, 3, 4 groups. So I have to have an 1s, p, and there's 3. So 1 plus 3 gives me a total of 4 there. Down here I have 1, 2, 3, 4, 5 groups. So sp3d, this all adds up to 5. And the last one, I have 1, 2, 3 groups. So this is an sp2 because my 1s and my 2 p's will add up. The last thing that we have to cover is polarity, whether something is polar versus nonpolar. What do those terms mean? Well, polar means that when they share these electrons, they are shared unequally. One atom pulls the electrons closer to it. So what are some things that would make a molecule polar? Well, if they're linear and those outside atoms are different, one side's going to pull more than the other. Another example of getting polarity is when there's a lone pair on the central atom. The only exception is if the shape is square planar or linear, or if molecules have different outside atoms. So there can be no lone pairs on the middle, but their outside atoms are different, it's going to be polar. Nonpolar is when they share these electrons, they're doing so equally. There's equal pull. So this happens when linear molecules and the outside atoms are the same, if there's no lone pairs on the middle, if they're square planar in shape, or if they have the same outside atoms. So if we look at these, here all the outside atoms are the same, and there's no lone pairs. So this is nonpolar. Here, the outside atoms are the same, but there's a lone pair right here. So this would make it polar. And this is not one of our exceptions. It's not linear and it's not square planar. When you look down here, the outside are the same, but you see these lone pairs. And so most people want to say that this is polar, but it's not. It's actually nonpolar because it's linear, in shape. And then last but not least, here we have 3 bonds, but the outside atoms are not the same. Here we have a different one. It's oxygen. So this one's actually going to be, oops. Sorry, guys. Let's get that up and running. So this one's actually going to be polar. And then I put acids and bases on your guys' paper. I want you guys to cross those out. I'm actually going to do a whole section of acids and bases when we get to that part in advanced chemistry, so I won't worry about reviewing that part. And that's the end of today's video. If you have any questions, please let me know, and I hope you guys have a good day.